Hello everyone, my name is MD Hasan Shahriar from Florida International University, presenting our work titled iDDAF, an intelligent deceptive data acquisition framework for secure cyber-physical systems. The authors are myself, Dr. Mohammad Ashiqur Rahman, and Imtiazul Haque from Florida International University, Dr. Badrul Chowdhury from the University of North Carolina at Charlotte, and Stephen G. Whisenant from Duke Energy. This is the outline of my presentation. First, I will go through the motivation, objectives, contribution of this paper. Then I will briefly describe the different attacks that we considered for this work and system and attack models. Then I will explain the proposed framework, iDDAF, which has two mechanisms. And then I will provide the evaluation results. And lastly, I will conclude the presentation. So cyber-physical systems integrate sensing, communication, processing, and control from cyberspace and the physical world. CPSs are everywhere in transportation networks, smart grids, water management, and so on. A new dimension for CPSs has been opened up by the Internet of Things, enabling real-time monitoring, data exchange, and optimal control. In this work, we consider power grids as the test case of CPS. So power grids has the remote equipments and energy management systems. The remote equipments can be IED, which is intelligent electronic devices or remote terminal units that sends the sensor data to the energy management system through the communication channel. And the energy management systems process the data using topology processor, state estimation, and finding the optimal power flow, and send the actuator signals back to the generators or breakers. So these control loops is executed through the communication channels here, which could be wired or wireless. The integration of the complex and heterogeneous systems in power grid CPSs creates enormous space for the adversaries. In most of the CPSs, the devices in the SCADA network have limited computational power to perform high-end encryption on the sensor data streams. Besides, some critical infrastructures like power systems have limited time constraints on the data acquisition process. For example, IEC 61850 enforces a maximum end-to-end time delay of 4 milliseconds, which is very difficult for any high-end encryption and for the lighted devices to ensure such latency. Moreover, several studies showed once a sophisticated attacker gains sufficient knowledge about the targeted system's topology and the states, he can easily evade the existing defense mechanism, for example, better detection algorithm, and mislead the state estimation towards his direction or his favor. And also, state estimation is vulnerable to denial of service attacks or missing data due to the unobservability issues. So to tackle these problems, our goal is to ensure the CIA triad for the power system or for any CPS. So the first thing is to ensure confidentiality by misleading the reconnaissance attacks, and ensure integrity by detecting and mitigating stealthy FDI attacks, and also ensures availability by mitigating denial of service attacks to ensure the system observability. So our goal is to ensure the complete security for any CPS control system. So to ensure the CIA triad, our contribution can be summarized in these following points. We propose a secure data acquisition framework, which here we introduce deception as defense for CPS network that makes the system resilient against cyber attacks. And we have two mechanisms, deception mechanisms, where we consider a complete randomization of the sensor IDs at the network switches, and we also add decoy data to support such ID randomization. And at the EMS, to restore the sensor data and run the state estimation on them, we use a prediction-based remapping, and that can remove the malicious data and fill up the missing data if necessary. So this is the background, little bit background that is needed to understand the project. So the state estimation and the beta detection algorithm can remove noises, remove random injections, and only consider good measurements to estimate the states. However, the false data injection attacks are very advanced attack that consider the system topology, and in that way it can compromise the measurement data by complying with the system topology, obviously, and such attacks cannot be detected by the ACBDD algorithm. So this is one of the advanced attacks specially designed for the CPS control loop. And another attack could be denial of service attacks. So this equation shows the least square regression based equation or model for the state estimation. Here H is the topology matrix which must have the full rank to use this equation. Here H, the rows of H represents the reported sensors and the columns represents the state vectors. Now any attacker whose target is to launch denial of service attack can target to make few of the sensor data unavailable, so that the H becomes rank deficit, and such equation cannot be utilized because the inverse function will not be working and the system becomes unobservable. This figure shows a hierarchical communication model of power grid SCADA with two layers of substation switches. Such hierarchy forms a tree structure where the sensor acts as the leaf nodes, substation switches as the internal nodes, and EMS is in the root. We define the sensors as level 0 elements of the network. A level 1 substation only receives data from its own sensors, whereas a level 2 substations receive data from both its sensors and the underneath level 1 substations. In a two-layered network, L2 switches directly report data to the EMS. The channel between the L1 and L2 switches is defined as L1 channel, and the one between L2 switches and EMS is defined as L2 channel. This slide shows the attack model. During the data acquisition process, there remains multiple vulnerable points which an adversary can compromise. In general, we classify an adversary's position into two groups. Firstly, the attacker can compromise the individual sensors. In this case, the attacker is sophisticated enough to be distributed to the edge nodes. We define such sensor attacks as L0 attacks. The second type is L1 or L2 attacks, where the attacker can compromise the network devices, especially the network channel. On the other hand, we also classify these attacks in two groups based on the attacker's steps. So the attack can be passive attacks or the active attacks. In case of passive attacks, the attacker's goal is to know the system states by snipping the data. And in case of active attacks, we consider FDI attacks and denial of service attacks. And in FDI attacks, the attacker injects malicious packets to mislead the state estimation. On the other hand, in case of denial of service attacks, the attacker drops few packets coming from some critical sensors, so that some part of the system becomes unobservable. That leads to the systems failing to run the state estimation process. This slide summarizes the literature review. There are a few works on introducing randomness in the CPS control loops, and also a few works suggested to perturb the system's physical properties using the defect devices to make the stealthy attacks invalid. And there are also few works on moving target defense with crafty network packets. These works are especially the MTD with the crafty networks only consider some subsets of the measurement data during the randomization, and most of these works are attack specific and do not provide a complete immunity. On the other hand, our proposed iDDAF can be implemented on the entire system, leaving no window for the attacker. Furthermore, iDDAF is the only framework that provides a complete security solutions CIA against three different types of attacks within a single framework. So this is the summary of the deception mechanism, And in this case, we considered three types of sensor. The first type is randomized. These sensors are considered for the ID randomization, and their IDs are shuffled among themselves during the data acquisition process. The second group is decoyed, and the framework adds decoy data for these sensors to support the ID randomization. And the last group is the fixed sensors, where there is no change on the sensor data or the IDs during the data acquisition. This slide shows how the ID randomization is done. So each of the deceiving nodes has a set of IDs. The first sequence is the rec IDs, and which is the received IDs, and random IDs or the rand IDs. Using this pair of IDs, any received sequence, which is irec, is randomized as irand using the algorithm rand ID. And also to support the ID randomization and make it hidden from the attacker, the framework also add the some decoy data using the find decoy algorithm. This slide shows the remapping mechanism. Here a prediction model is used based on the historical state data to predict the next state vector. In this case, we consider a second order polynomial regression model and multiply the predicted state vector with the topology matrix to get the predicted measurement vector. Then we utilize an optimization algorithm or optimization. We create an optimization problem to find the original or the best set of remapped data from the reported data, considering the predicted data. And then if the remapped data is sufficient for observability of the system, then that is enough for the state estimation. Otherwise, data imputation is needed, and the missing data is replaced with the predicted one, and then state estimation and better detection algorithm can fine-tune the data and consider that for further decision-making task. This slide summarizes the remapping algorithm and some snapshot of the constraint that we considered. We considered a combinatorial optimization problem using mixed integer programming. Here our goal is to maximize the measurement assignment while minimizing the recovery loss. And this slide shows a 14-bus case study. Here the purple color shows the reported data for 54 measurement factor for 54 measurements for IEEE 14-bus system, and the yellow one shows the predicted data, and the green color trend shows the recovered data, recovered data from the reported one. And we see that the yellow color, the predicted one, and the green color, the recovered one, perfectly follows the same trend, and that means that our remapping algorithm is almost accurate in recovering the measurement data. On the other hand, if there is an FDA attack which is done on the IDs shown with the red color, so say for example ID 5, ID 6, and 26, 27, and so on, and we see that the remapping algorithm accurately actually skip this measurement data or IDs during the remapping mechanism, and only consider the good data in the remapped one. So we have the evaluation here. So first we evaluate the framework against reconnaissance attack. So we consider IEEE 14-bus system, and we take 60% sensors as randomized, and the remaining 40% we change the percentage of decoyed sensor and see the impact against the reconnaissance attack. So the first graph shows that without any decoyed sensor, even though we have 60% random sensors, the attacker was able to see or estimate the trend of the states with a very high degree of accuracy. But if we add 40% decoyed sensor along with the 60% random sensors, now the randomization is supported by the decoy data, and attacker fails to detect the state estimation. However, in both the cases, the EMS is able to estimate the state perfectly using the remapping algorithm and without any kind of deviation. The last graph shows the impact of decoyed sensor on the state estimation, on the attacker state estimations. Here RD stands for reconnaissance deviation, which is the difference between the attacker's estimation and the actual estimation. And we see that as we keep adding more decoyed sensor, the attackers get deviated from the from the original state estimation for level 1 and level 2. So this slide summarizes the impact or the robustness of the framework against FDI attacks. The first graph shows the impact of single-step FDI attacks. So in this case, we consider or we implemented FDI attacks in every 30 time steps, and see the impact of randomized sensor against the ED, which is the difference between the EMS state estimation and the actual state estimation. So our goal is to minimize the estimation deviation and get back to the original state estimation. So as we see that if we keep increasing the percentage of randomized sensors, we see the estimation deviation decreases towards 0. On the other hand, we also evaluated the impact of estimation deviation for different length of FDI attacks. As we see, with 0% with 0% randomized sensors, if the attack duration is higher, the impact also gets larger due to the cascading effect. However, if we keep increasing the randomized sensors, that ED or the cascading effect goes away, and ED becomes almost 0. The last evaluations on the denial of service attacks. So the first graph shows the percentage of unobservable cases due to denial of service attacks. That means how many times the systems becomes unobservable. So the first graph is for the seed-based or sharing-based remapping algorithm, where there is no intelligent imputation algorithm to come up with the missing data. So in this case, we see that for L0 denial of service attacks, all the attack vectors make the system unobservable, and for L2 attack, the system achieves very low PUC, but the L1 has very serious issues for 20% cases. On the other hand, our proposed iDDAF with data imputation can tackle all the issues or any denial of service attack at any level, because it has the capability of replacing or filling the missing data with the predicted one, and can effectively mitigate 100% denial of service attacks, and leaving PUC to 0% for all the levels. So that's the end of my evaluation. So to summarize the paper, we have proposed a deception defense based data acquisition framework, which is titled iDDAF, that achieves the CIA goals for the control for the cyber physical systems. In this case, we consider the ID randomization and adding decoy data to mislead the attacker. We propose an intelligent remapping technique to store the data at the EMS. And iDDAF can detect, mitigate different cyber attacks. That our evaluation results on IEEE 14 systems show that the framework is scalable and effective, and with sufficient deception, iDDAF can provide almost 100% immunity. This work is supported by NSF, and thank you everyone for your patience. If you have any questions, I'd be happy to reply your answers. So here is my email. Thank you so much.